Problem 2 will be a laboratory design problem involving comparators. This particular problem is very real world. It involves these two inputs, a logic battery that you want to test. And whenever this logic battery that powers the microcontrollers of your robot goes below 5 volts, the robot starts acting weird. And when it acts weird, you don't know if it's a problem with the way you've programmed it or just the simple fact that the battery is low. So you want to modify your power supply. So it turns on a bright LED whenever the voltage on this logic battery goes below 5 volts, because soon after that, your robot's going to act weirdly. You've also got a separate battery that's 12 volts, and you can rely on that being a good 12-volt source. Your output is going to be a single LED. It drops 2 volts, and it runs at 20 milliamps. So your problem is, given these things, how do you design a circuit using a comparator that will turn on this LED to the right whenever the voltage on your logic battery drops below 5 volts? So before we begin, we should probably talk about what makes a comparator different than an op-amp, given the fact that the schematic symbols look exactly the same. So here's the schematic symbol for either one. And we'll call the non-inverting input V plus, the inverting input V minus, and we've got the V out over here. So for a op-amp, which is not what this problem is about, the governing equation is that V out is equal to some variable gain A times V plus minus V minus, where A is huge. It's tending towards infinity. For the op-amps we have in the lab, it's maybe 100,000 to 1 million. It's pretty big. The point is that if you have this voltage, if you have V plus, which is slightly greater than V minus, you can think about that as being the on condition, the condition that the op-amp wants to be in. And when it's in that on condition, when it's in that normal condition, it's going to try to put out an infinite amount of voltage. But you know it can't, because it's going to be connected between a positive and a negative source. Now, for this particular problem, we don't go below ground. We can't go above 12. So if V plus is greater than V minus, it will try to produce an output that's huge variable gain A times V plus minus V minus, which will try towards tending to infinity. The highest it can go is 12. So the output will be 12. In the related case, where V plus is less than V minus, so this is what we want to think about as the off case. Now, this number is going to be negative, so V out will tend towards negative infinity. The lowest it can go, since it's powered from ground to plus 12, is going to be ground. So therefore, the output will be 0 volts. And again, this is the case for the op-amp. Now, let's talk about what the case is for the comparator. We have the same type of symbol. It's powered the same way. We've got the same two possible conditions on the inputs, that V plus can be greater than V minus, or V plus can be less than V minus. And because that's a mouthful to say, I find it, again, helpful to think about it in terms of the on state, if it was an op-amp, or the off state, if it was an op-amp. But comparators work differently. When a comparator is on, the output is disconnected. That's not 0 volts. A 0 volt output would be as if the op-amp is connected to ground. And it's not 12 volts. A 12 volt would be as if the op-amp's connected to 12 volts. But when it's disconnected, it's as if the op-amp wire just goes to nothing inside. For the op-amp version, this can be driven by, you can put anything you want over here, and this will still be 12 volts. For the op-amp version, in the off case, it will be 0 volts on the output. For the comparator version, in the on case, it can be any voltage on the output because it's not connected to anything. However, the off case is the same as the op-amp version, and it does look like a ground. So this is the difference between the way that an op-amp works on the left and a comparator works on the right. Now, given that, let's start to examine our circuit. What we know is we need to have this op-amp here. And you can draw the plus on the top or the bottom just arbitrarily. I'm going to start off with it on the plus. we need to power it. So I'll power it from the supplies we're given, which is a 12 volt. Of course, this is just a shorthand for a much more ugly version of doing this, because then we've got to have this output doing stuff, and that will just look ugly. So I'm using the shorthand to keep it clean. And now let's begin designing. Let's start off with the output. If this was a op amp, we might be tempted to do something like this. But this won't work as a comparator, because if you're in the on state, and remember, these on and off states, they're talking about what the comparator is doing, not necessarily what the output is doing. When the comparator is in that nice on state, V plus is greater than V minus, then the output is going to be disconnected inside, and the LED will be off. But in the opposite case, when we're in the off case, the output will be grounded and the LED will also be off. So the way we've drawn it, either way, that LED is going to be off. That's not a very useful circuit. We might as well just not hook up the LED at all. And so we can't use it. Instead of tying that LED low, we are going to tie that LED high. The arrow on the LED still has to point down, this arrow, because it always goes in the direction of current flow. But now, one way when it's disconnected, the LED will be off, and the other way when it's grounded, current will flow through to ground, it'll be on. So at least now it can do anything. Unfortunately, it's going to destroy the LED. You can see this because in the off case, where the op amp's output looks grounded, it looks like it's doing this inside. You've got a full 12 volts across that LED. But the LED is only rated for 2 volts across it, so it'll immediately burn up the LED and it won't work. So we're going to have to do something to control the amount of voltage across it and the amount of current through it. And to do that, we'll stick in a resistor. So you can put the resistor in either side, above it, before the diode, or after the diode. I'll do it afterwards. And to figure out how big a resistance we need, we can use Ohm's law. So Ohm's law says it's equal to the voltage across the resistor divided by the current through it. Now, when the diode is on, when the LED is on, we have 12 volts up here, but we said it drops 2 volts. There's 2 volts difference between the top and the bottom. So when this thing is on and there's 2 volts across it, that means that if it's on, so we're grounded over here, and this is 0 volts, we'll have 10 volts across the resistor. So to be really pedantic about that as I draw it in, I could say it's equal to 12 minus 2 volts, or 10 volts across the LED. And the current through it is going to be 20 milliamps. So we can process that pretty easily. That's equal to 10 over 0.02. So that's going to be 500 ohms. That's the first part of our design. Next part is we have to worry about the inputs now that we've got the outputs figured out. So let's draw what these inputs look like. These 2 inputs have to be voltage sources. I'm going to draw them as, I'm going to start off with a logic battery. And this is the thing we want to test. Arbitrarily, I'm going to put a plus on top and a minus on the bottom. You can draw it in either direction. Not going to forget to power this thing. We've already worked out what the output should look like. Now we want to drive the input. So we want this LED to turn on or turn off when the logic battery's voltage crosses a 5 volt threshold. So therefore, we want to develop 5 volts across here. And this way it will test this 5 volts relative to the logic battery. And when it's greater or less, then it'll do something different out here. And the way to create that 5 volts from your 12 volts is with a voltage divider. So there's different ways we can make this voltage divider. In the problem, you can use any kind of resistors you want, but all the resistors, I'm going to add that as a restriction up here. All the resistors in any kind of reasonable design we're going to say are going to be between 1 kilo and 1 mega ohm. If the resistors are too small, let's just take it as a reductio ad absurdum argument. They're equal to a fraction of an ohm each. Well, at a fraction of an ohm each, you're going to have amps going through this. Just resting, you're going to have amps shooting straight through all the time, and you'll have a huge amount of power lost. In fact, if you have, say, 10 amps flowing through this, 10 amps times 12 volts means you're going to be dissipating 120 watts, about that of a bright, hot light bulb just sitting at rest. In no time, you'd have your car battery discharged. On the other hand, if you go the opposite way and make the resistors ridiculously big, hundreds of giga ohms, then just simply touching that resistor is going to put finger oils on the outside, change its resistance, so that's a bad idea. But this still gives you this range from 1K to 1 mega ohm, gives you a huge range of values to work on. So let's come up with the equations. We know from the voltage divider equation that we want 12 volts times this 5 volts is the voltage across the R2. So that would be R2 over the sum. We want that to equal 5 volts. That's our only equation we have. If you satisfy this equation with an R1 and R2, such that R2, the R's are reasonable values, you've solved the problem. But you can't solve that uniquely. You've got two unknowns and you've got only one equation. So you have to come up with another equation. Now, the sort of the grind the crank way of doing it is to say, ask yourself, you can see that there's going to be some current that shoots through here, that shoots through in this direction. And that's always going to be shooting through. No current ever goes into the comparator. So this current's just wasted. And it's not unreasonable to say you'd like to minimize that amount of current. But if the current's too small, you'll run afoul of the resistors getting to be too big over here. So you might say, let's just keep this current to something small. Let's keep it to, say, arbitrarily 1 milliohm. And so our 12 volts over R1 plus R2 equals 1 milliohm. And then let's see how that works. And if these R's are in this range, it works. And if these R's aren't in the range, if the R's are way too big, well, then we'll adjust this number bigger or smaller until the R's get in the range. This is a perfectly good approach. I'm going to rewrite this a little bit more clearly. My handwriting gave out there. R1 plus R2. Now it's clear. So now we've got these two equations and two unknowns, and this is not an incorrect solution, but it's not the way that I would do it, because I'd have to drag out the calculator. And although you can solve this using 8th grade math, it's easy to make an algebraic mistake. The way that I would solve it is I would ignore this bottom part and I would just look at this top part of the equation. And I'd say, if we made this part down here equal to 12, then that 12 and this 12 would cancel, and we just have R2 equals 5. In other words, if we just had R1 plus R2 equaling 12, then we know R2 would have to equal 5 to make this work. And then from the top equation, we know R1 would have to be equal to 7. And that's a solution, except it doesn't fit in this range. It's not nearly 1K to 1M. So how to fix that? Just put a K on the end, multiply them both by Ks. And now everything is still perfectly valid. Our equations will just be this. So that trick is called resistor scaling. If you can find a purely resistive circuit that works, just like a voltage divider equation, if you've got a voltage divider equation with two 1 ohms or two 1Ks or two 1 megas, either way, it is going to be a perfect voltage divider. Now we've solved the entire problem. We know our R1 is going to be 7K. We know our R2 should be 5K. That's in the range here. And now let's just double check that everything works out. By the way, obviously, you could have come up with a different value of these. In fact, any value of resistors that you come up with, such that the ratio between them is 5/7 will work, as long as this criterion is met. So now let's just check out that it works. When the logic battery is less than 5 volts, what happens? And we can check out when the logic battery is greater than 5 volts. When it's less than 5 volts, we know this will always be 5 volts. This will be less than 5 volts. So now we know that V plus will be greater than V minus. If the logic battery is okay, then our V plus would be less than V minus. So this is saying that the comparator is in the on version. If the logic battery is greater than 5 volts, it would be in the off version. Now, what the comparator is thinking of on or off is not necessarily what's turning the LED on or off. It's just telling you if it's in this disconnected version or this 0 volts version. The comparator output, when it's on, is disconnected. And when it's off, it's grounded. Now we can check out how that LED is doing. If the output of the comparator is disconnected, this LED will be off. Here, the LED will be on. And that's unfortunate because that's the exact opposite of what we want. So how do we fix that? To flip it around, we just change these signs. And now the top is minus, the bottom is plus. And now these signs would be inverted. If the logic is less than 5 volts here, then our V plus will be less than V minus. In this case, it'll be greater. This top part is always 5 volts. This bottom part changes depending upon what the logic battery is. And now the comparator sense of what's on or off is flipped. Therefore, the comparator's output sense is flipped. Now here, when the comparator's in this stage, the comparator is in that off-like version, so the output is going to be grounded. And here it's in the on-like version, so it's going to be disconnected. When it's disconnected, there's no place for the current to flow, so the LED will be off. When it's grounded, current goes through the LED to ground, and it's on, and this solves the problem.